get started today. So we'll be recording this and it'll be uploaded later for folks to review as well as folks that can't attend. But welcome and thanks everyone for joining us. I'm Drew Miles, one of the head deputy secretaries and one of the co-organizers of the Head Frontier seminar series, along with Javier Garcia, who's here, and Carolyn Kierans. So the Frontier seminar series is this virtual series of seminars that we have where we try to give opportunity for early career members of the Head community to give talks on their research and sort of get their research out there to a broader audience as part of our community. So thanks again for joining us. This is our first one of this year, and we'll notionally plan to do these every 2 or 3 months or so for about an hour each time. And today we'll have 3 separate talks. Each one will plan for about 15 minutes for the speaker, and then we'll have a few minutes of question and answers. Please use either the chat function for questions or the raise hand function. And then Javier and I will try to call on folks or point out questions in the chat for our speakers. So with that, we'll go ahead and get started with our first speaker today, which is Julia Speicher, a grad student at Georgia Tech. So Julia, please feel free to share your screen and take us away.
Okay. So you can all see the screen. So hello everyone. So my name is Julia Speicher and I'm a grad student at Georgia Tech. The title of my presentation is Type I exobursts as probes of a neutron star accretion environment. And in this presentation, I will tell you how Type I exobursts impact the neutron star accretion flow and affect its emission. But first, I will give you a quick review of Type I exobursts. Type I exobursts occur for neutron stars in low mass X-ray binaries, where the neutron star accretes matter from another star via Rashlob overflow. This accreted material, mainly hydrogen and helium, accumulates onto the neutron star surface, and this ongoing accumulation causes the temperature and the pressure to increase in this accumulated layer. Eventually, conditions for unstable nuclear burning are met, and the accumulated material is burned within seconds, causing a Type I exoburst. The Type I exoburst shows up as an exponential increase in the X-ray count rate, followed by an exponential decay, usually lasting of of seconds. An example of such a light curve, as observed with NICER, can be seen in this figure here by Kiek et al. From 2018. During such a Type I exoburst, an enormous amount of radiation is emitted into the neutron star environment, and there it will interact with the neutron star's accretion flow. And for this presentation, I will talk about the interaction with the corona and the accretion disk. First, I will talk about the interaction of the burst with the corona. Just as a quick reminder, the corona is an optically thin but geometrically thick region of hot electrons. Its position and structure is not clear yet. One model suggests that if a neutron star has a low mass accretion rate, then the corona is between the neutron star and a thin truncated accretion disk. Observationally, the corona compton upscatters the soft photons coming from the accretion disk and the neutron star, and so it contributes a hard X-ray power law to the observed emission. During bursts, it has been observed that this hard X-ray emission decreases, which can be an example of this can be seen in this figure here, showing stacked light curves for different energy bands. In this figure, you can see that while the light curve corresponding to the soft X-ray band between 3 and 20 keV increases during the burst, the light curve corresponding to the hard X-ray band between 35 and 70 keV decreases. It has been suggested that this decrease of the hard X-ray emission during the burst is due to the burst photons cooling down the corona. This coronal cooling has been investigated in theoretical work, such as simulations. In 2018, Fragile et al. Simulated a thick accretion disk representing a corona being impacted by a Type I exoburst. Here are resulting figures from their simulations. These figures show the temperature of distributed in space, time averaged over half a second interval. On the left, for a simulation where no burst occurred, on the right for a simulation with a burst. By comparing these two figures, you can see that the presence of the X-ray burst caused significant cooling of the simulated corona. Fragile et al. Found that the temperature dropped by over 3 orders of magnitude due to the burst photons compton cooling down the simulated corona. As you can also see by looking at these figures, this coronal cooling also led to structural changes. Because the simulated corona was supported by thermal pressure, the loss of temperature caused it to collapse. While this simulation outputs how the coronal properties change during the burst, it does not output what the observational consequences of this coronal cooling will be. And this is something that we investigated in 2020. For that, we set up an analytical model where we assumed that the corona is powered by accretion luminosity dissipating in it, and it is also irradiated by some soft luminosity coming from the disk, the neutron star, and then also the burst. For this model, we calculated the coronal electron temperature and the coronal spectrum with a hybrid emission plasma code AQ pair. And because we wanted to see how the coronal cooling depends on properties for our calculations, we varied the strength of the burst, the coronal aspect ratio, so height divided by radius, and the coronal optical depth. Here are some of the resulting spectra from our calculations. For these coronal spectra, the burst luminosity has been varied. And from this figure, you can see that as the burst gets stronger, there will be more coronal cooling, which leads to a greater decrease in the hard-X emission. Besides being dependent on burst properties, coronal cooling also depends on coronal properties, which you can see by looking at this figure here. For this figure, we kept, for these coronal spectra shown in this figure, we kept the burst luminosity constant, but we varied the coronal aspect ratio. And from this figure, you can see that if a corona has a greater aspect ratio, then more burst photons can enter the corona, which leads to more coronal cooling and therefore a greater decrease in the hard-X emission. Therefore, because coronal cooling depends not only on burst properties, but on coronal properties as well, studying how the hard-X emission evolves during the burst could be a way to infer these coronal properties. Besides interacting with the corona, the X-ray burst will also interact with the accretion disk. And one way this can be seen is by looking at the accretion disk reflection spectrum. The reflection spectrum is caused by the accretion disk being irradiated, and in the case of a burst, the main source of this irradiation comes from a burst. This irradiation causes reflection features, such as emission lines, for example, an iron K-alpha emission line between 6 and 7 keV, and a reflection continuum. An example of the reflection features can be seen in this figure here by Kike et al. From 2017. The top panel shows a burst spectrum as observed with SWIFT, which has been fitted with a black body, and this black body fit follows the blue dotted line. The lower panel shows the residuals of this black body fit. In this observation, Kike et al. Found an emission line at around 1 keV. Another feature that you can see here, which has also been observed during our burst observations, is the soft axis. While it has been suggested that the soft axis could be due to reflection, another proposed reason for it is the increase in mass accretion rate. But for now, I will only focus on reflection. I will come back to the mass accretion rate later on. These reflection features depend on the accretion disk, and so studying how the reflection features evolve during the burst is a way to infer changes in the accretion disk structure from it. How the accretion disk structure changes during the burst has been investigated in theoretical work and again through simulations. In 2020, Fragile et al. Simulated a thin accretion disk being impacted by type 1 X-ray burst. And here you can see resulting spacetime diagrams from the work. For these spacetime diagrams, for every radius as a function of time, the density-weighted surface density has been plotted. On the left for a simulation where no burst occurred, on the right for a simulation with a burst. Fragile et al. Found that in their simulations, the burst irradiation caused the accretion disk temperature to increase, and this heating caused the accretion disk to inflate, which decreased its density and optical depth. Another consequence of this disk-burst interaction that you can see by looking at these spacetime diagrams is that during the burst, the inner disk radius retreats due to the increase in the mass accretion rate, which removes inner disk material faster than the accretion disk can replenish it. But I will talk more about the mass accretion rate at the end of the talk. As it was the case for the simulation with the corona that I already mentioned, this simulation does not output what the observational consequences of this disk-burst interaction will be. And this is something that we studied in 2022. Specifically, we were interested in how the reflection spectrum evolves during the burst. For that, we used the simulation data from the simulation I mentioned on the previous slide. And for different time intervals along the burst evolution, we got time average simulation data. For each of these time intervals, we first defined a reflecting region, which we then sectioned further into radial zones. An example of this setup can be seen in this figure here. The colors of the color map correspond to the hydrogen number density. The black solid lines bound the reflecting region of the respective time interval, and the red dashed lines section of these radial zones, which we call 0 through 6. For a given time interval, we first calculated the reflection spectrum for each of these radial zones, and then to get one reflection spectrum per time interval, we integrated these individual reflection spectra up. These integrated reflection spectra for different time intervals along the burst evolution can be seen in this figure here. The black solid line shows the reflection spectrum, and the red dashed line shows the emission of a burst irradiating the upper surface of a respective reflecting region. And you can see by following the reflection spectrum evolution by moving from left to right that as the burst gets stronger, the disk gets increasingly ionized, which weakens the emission lines. We were also interested in the soft axis due to reflection. This figure here shows the percentage of soft axis below 3 kV as a function of time. And we found that for our calculations, the soft axis increases during the burst, which is on the one hand due to the burst photons getting increasingly energetic, causing more Compton scattering, and also the accretion disk getting increasingly heated, which generates more Bremsstrahlung photons. Therefore, our work showed that reflection is capable of producing a strong soft axis. Another reason for the observed soft axis during bursts is the increase in the mass accretion rate, which I will talk about now. In 2013 and 2015, Werbel et al. Tried fitting the persistent emission with a variable normalization factor. And we found that using such a variable normalization factor not only improved the fit, but that this normalization factor also often exceeded 1. An example of this use of a normalization factor can be seen in this figure here by Keith et al. From 2018. The top panel shows the light curve during an X-ray burst, and the bottom panel shows this normalization factor, often called FA, during that time. And you can see that it increases as the X-ray count rate increases. It has been suggested that this increase in the normalization factor is due to the increase in the mass accretion rate, which increases the persistent emission and is a potential cause of a soft axis. The physical reason behind the increase in the mass accretion rate is the special relativistic effect called Poynting-Robertson drag. Poynting-Robertson drag exerts a drag force onto the disk material, which therefore loses angular momentum and falls faster towards the neutron star. The increase in mass accretion rate has also been studied in the simulations by Fricke et al. In 2020. This figure here shows the mass accretion rate from a burst simulation for different simulation setups divided by the mass accretion rate from a no-burst simulation as a function of time. And in their work, they found that the mass accretion rate was enhanced by over an order of magnitude. However, in their simulations, they assumed that the neutron star does not spin. And this can have an impact on the inferred significance of Poynting-Robertson drag. Because if a neutron star has a prograde spin, Poynting-Robertson drag is expected to be weaker, because then the relative velocity between the disk material and the burst radiation will be smaller. Therefore, one could ask a question, if a neutron star has a spin, how important is Poynting-Robertson drag? Will it still be strong enough for potentially increasing the persistent emission and causing a soft axis? We wanted to answer these questions, and the way we did it is by running simulations where a neutron star had a spin and comparing them to simulations where a neutron star did not have a spin. This led to this figure here. This figure here shows the moving average of the mass accretion rate enhancement for the spin and the no spin case as a function of time, as measured at the respective radius of innermost stable circular orbit. And in this figure, you can see that as measured at the respective radius of innermost stable circular orbit, the mass accretion rate actually got more enhanced in the spin simulation than in the no spin simulation. A reason for that is that Poynting-Robertson drag this is not only spin, but also distance dependent, because it depends on the flux that the disk material receives. This can be illustrated with this figure here. For this figure, we calculated for an analytical model the angular force due to Poynting-Robertson drag for the spin and the no spin case as a function of distance. And from this figure, you can see that if you would compare the angular force due to Poynting-Robertson drag at exactly the same radius, you would get the anticipated result, but it is stronger if the neutron star does not spin. However, then you have to take into account that the accretion disk will be closer to the neutron star if the neutron star spins. Therefore, it will receive a stronger flux, which can offset the weakening impact of spin. Therefore, Poynting-Robertson drag will be important with and without the presence of neutron star spin. To conclude, TAP and exobursts impact the accretion environment of neutron stars. For coronae, they cause a decrease in the hard X-ray emission, which can be explained with coronal cooling. Because this coronal cooling depends, besides on burst properties, also on coronal properties, Studying how the hard X-ray emission evolves during reburst could be a way to infer these coronal properties. Regarding the accretion disk, people have observed reflection features, a soft axis, and a potential increase in the persistent emission during reburst. In our work, we found that as the burst gets stronger, the accretion disk gets increasingly ionized, which weakens the emission lines, and that the reflection is capable of reducing a strong soft axis. Regarding Poynting-Robertson drag, Poynting-Robertson drag will increase the mass accretion rate and will be important with and without the presence of neutrons for spin. Therefore, it remains a viable explanation for explaining the potential increase in persistent emission and the soft axis. Yeah, thank you.
All right, thank you, Julia. So we mentioned in the chat, please use the raise hand feature, or feel free to put your question in the chat. And we have a few minutes now to take questions for Julia. Okay, Javier, see you with a hand up.
Yeah, Julia, thank you. That was a great talk. I'm very impressed with all the things you've done in such a short amount of time. I have many questions, but we can talk with more length later. But right now, I was wondering if you can tell me something about what's the typical density in the fragile simulations and in the accretion flow that you're considering here, because that might be connected also with how the reflection explains the soft excess. I don't know if you have that information. You show in one of your slides the column density of the gas, but do you know what it will be? Just the particle density, typical.
I don't. Yeah, sorry. I don't remember right now what the typical particle density is in the simulation.
Yeah, because what we've seen from reflection modeling is that when you increase the density, Bremsstrahlung emissivity increases quadratically with it, so it takes over and produces lots of soft excess in a model that for the same ionization, say, will show differently. So maybe something for you to check.
Okay, we have a question in the chat from Chris Schrader. Could the irradiation of the disk lead to a limit cycle instability and thus an increase in m dot and soft excess?
What is meant with an so with a limit cycle instability?
Chris, if you're able, feel free as well to unmute.
Hello?
Yep, we can hear you.
Hi, no, just accretion disks, like accretion-driven transient events and certain CVs, dwarf novae, and in the black hole X-ray binaries are believed by many to be triggered by a jump in the stability curve, so-called limit cycle instability. I'm wondering if that could be at play here, because you have the extreme heating of the disk from the from the type 1 event.
I'm not sure. So
It's okay, thanks.
yeah. So I'm sorry. So I'm not so familiar with this instability, and so I'm not sure how it affects the mass accretion rate.
Okay, thanks, Chris. And we'll go ahead and transition now to our next speaker. So thank you again, Julia. And our next speaker will be Fan Zhao, a PhD candidate at Penn State, and is actually about 1 month or so from graduating, so preparing for the dissertation defense, and then we'll be taking a postdoc position at Michigan. So Fan, please go ahead and share your screen and take us away.
Yeah, great. Thank you for the introduction. Yeah, so today I'm going to talk about how do supermassive black holes grow from ratio of 4 to ratio of 0. It's a broad topic, and we know that there are two basic growth channels for supermassive black holes. One is accretion, where supermassive black holes connect with the surrounding gas and shine out as the so-called active galaxy nuclei. And the other channel is mergers, where two supermassive black holes can merge into a single, more massive one, following the dark matter halo and host galaxy mergers. So to understand the whole, to gain a holistic understanding of the supermassive black hole growth, we need to understand both channels. And I will talk about the first channel, the accretion channel, and then talk about the mergers in the second part. So for the accretion-driven growth, it has been shown that this channel is strongly correlated to the host galaxy properties. And let's first define a parameter called population mean black hole accretion rate, or BHAR. And this parameter is just defined as the black hole mass increasing rate averaged over the whole galaxy population. And it has been shown that this parameter is strongly correlated with the stellar mass and redshift for the general galaxy population. So this function, the black hole accretion rate, the mean black hole accretion rate as a function of stellar mass and redshift, can directly quantify the relationship between the supermassive black hole growth and the galaxy properties. And so we aim to provide the best measurement for this relationship. But how do we constrain that? Here is a very basic summary of the methodology. So first, we need to measure the so-called accretion distribution, or P lambda. And this is just the conditional probability density of a galaxy with a given stellar mass and redshift, hosting an AGN with given lambda. And lambda here is defined as the X-ray luminosity divided by stellar mass, which is just a normalized accretion rate and roughly scaled with the Eddington ratio. And then the black hole accretion rate can be calculated by this equation. And here we have the factor times the X-ray luminosity. And this factor converts the X-ray luminosity to the mass accretion rate, and then we average over the accretion distribution. So we do an integration to average that, and in this way we can obtain the population mean black hole accretion rate. And you can see during this process, we need X-ray data to sample the AGN accretion power, and also we need multi-wavelength surveys to sample the galaxies. So actually, the data is quite demanding here, and to obtain a reliable results on this, we have done a lot of work in compiling the data, and we have constructed a very large sample from 9 deep fields, including this follow the wedding cake design. So we include both deep pencil beam surveys like the candle fields, and also wider and shallower surveys like LSST deep drilling field and the new EFET field. So actually there is a lot of work behind this single slide, and our sample is at least like 10 times larger than previous works on this matter. And besides the data, we also developed a new method, and we call it the semi-parametric Bayesian method, to actually measure the black hole accretion rate in the stellar mass redshift plane. And the basic idea is that we have the best data and the best methodology, so we can naturally obtain the best measurements of the population mean black hole accretion rate, and this can last for many years. And I've given the methodology here, but here is I'm directly showing the results, how the black hole accretion rate evolves with stellar mass at different redshifts. And you can see that it generally increases with both stellar mass and redshift. And if we plot the black hole accretion rate in the stellar mass redshift plane, we can obtain a nice 2D map showing the mean accretion rate. Okay, and besides the population mean, the BHAR, we have also obtained, as I mentioned earlier, the accretion distribution of P lambda. And here I'm showing the accretion distribution at different stellar mass and redshift. And this is these two slides are our main results, and they are the fundamental, quite fundamental, and many more scientific questions can be addressed with these results. And I'm going to show you some quick examples to illustrate that. So first, for example, if we convolve the accretion distribution with the galaxy stellar mass function, then we can obtain the so-called X-ray luminosity function. Here I'm showing our predicted X-ray luminosity function with the actually observed X-ray luminosity function. You can see that generally agree pretty well. So this indicates that our accretion distribution is generally quite reliable. And also, with the accretion distribution, we can immediately obtain the fraction of galaxies hosting AGNs, because this quantity is just an integration of the accretion distribution. So here I'm showing the AGN fraction versus redshift at different stellar mass beams. And actually, you can see the dependence is quite complicated. And at the low redshift, the AGN fraction is almost independent with stellar mass, but at high redshift, more massive ones evolves more with redshift and then reach a plateau, but the less massive ones is more or less follow a flat trend with redshift. So this is also quite interesting finding. And also we did our measurements separately for star-forming galaxies and also quiescent galaxy population. And the blue one, the blue curves here show the black hole accretion rate for star-forming galaxies, and red curves show the value for quiescent galaxies. And you can see that the blue curve is generally above the red one, so that indicates that star-forming galaxies tend to have stronger supermassive black hole growth. And this is also interesting. So, but overall, I'm just showing some quick examples illustrating how our results can return some interesting scientific can help address some interesting scientific issues. And but this work mainly focuses on presenting the actual results of the black hole accretion rate and the accretion distribution, and we leave most of the scientific investigations to the future work and together with the physical explanation. But in the second part, I'm going to talk about one important implication based on these results of our depiction of the accretion channel. That is, we will add the merger channel into the consideration, so that we combine accretion and merger, then we can build a complete picture of the supermassive black hole growth. And for the accretion, as I mentioned earlier, we just use the observationally merged accretion channel from our previous work, and then we add merger information from the Illustris TNG cosmological simulations. And here is a picture from the TNG website, just showing how it can capture both the large-scale structure and also probe each individual galaxies. And there are actually very important motivations here on why we use an observationally constrained accretion and simulated mergers. So that's because the merger channel can hardly be directly observed. So that's why we use simulations to obtain the merger information. But on the other hand, the simulations usually cannot reproduce a reliable supermassive black hole population that is consistent with observation. So that means the simulated accretion channel is not reliable, and I will talk about that later. So that's why we use the observed accretion channel and the simulated merger channels, and in this way we can take advantage of both of them, and so that we can provide the most realistic picture of the whole supermassive black hole growth. Okay. And our basic approach is summarized by this single equation. It's quite straightforward. So let's say if we have a supermassive black hole with black hole mass of MBH at the redshift Z, and when it evolves from redshift Z to Z minus delta Z, then the black hole mass will increase by 2 terms. One is the accretion through the accretion channel. This is just the black hole accretion rate times the time interval. So this is the accreted mass, and then the last term is the merger induced, the merger added black hole mass. So we just add them together. In this way, you can obtain the predicted black hole mass. And here I'm showing 2 example evolutionary tracks of the simulated galaxies in the TNG simulation in terms of their stellar mass and the black hole mass. And these stellar mass evolutionary tracks are shown as these cyan lines. And then we follow this stellar mass evolutionary track, and we apply this equation to these stellar mass evolutionary tracks to obtain the predicted black hole mass evolutionary tracks. And we do that for all the simulated galaxies in the TNG simulation. And in this way, we can obtain the expected black hole supermassive black hole population at different redshifts. And here I'm just showing 2 examples. One is less massive and one is more massive. And you can see that the more massive one clearly undergo many more mergers. Okay. So with the predicted supermassive black hole population across the whole redshift range from 0 to 4, we can do a lot of interesting measurements. For example, we can obtain the so-called black hole mass function, which is just the black hole number density as a function of black hole mass. And here I'm showing the black hole mass function at the redshift of 0, and these blue ones are all our measurements. And I'm also showing some other measurements in previous work, and you can see that generally agree pretty well. And I also want to mention that these black open points are the TNG black hole mass function themselves. So TNG also includes the supermassive black hole population, but their black hole mass function is far above than the actually observed one. So that's my point, that their recovered supermassive black hole population is not that reliable. And with our post-processing, we can obtain a more robust supermassive black hole population. And that's the local black hole mass function. And then we can also obtain the black hole mass function at different redshift from 4 to 0. And you can see that the black hole mass function increases from redshift 4 to 1, and basically locks down and shows very little evolution from redshift 1 to redshift of 0. And that's also an interesting finding. And that's the black hole mass function. And we also predicted the scaling relationship between the black hole mass and the host galaxy stellar mass. And here I'm showing the scaling relation at different redshifts together with some like observationally constrained scaling relation. And first, we can, again, our measurements are also quite consistent with other observationally constrained measurements. And also, our scaling relations do not show strong evolution from redshift 4 to 0. So that's our prediction. We predict that at least out to redshift 3 or 4, we shouldn't expect to see a very strong evolution in the scaling relationship between the black hole mass and the stellar mass. And also we also measure the accretion, the growth rate in each channel. Here I'm showing the growth rate versus stellar mass in the accretion channel, which is shown in the blue the red curves, and the blue and the cyan curves showing the merger-driven growth rate. And these blue one, these red ones are just our accretion, our black hole accretion rate in the first part of this talk. And with our combination from the TNG, we can obtain the merger-driven growth. And you can see that generally the red curves are far above the blue and cyan curves. So this indicates that accretion channel usually dominates over the merger channel in most cases. But there are some exceptions, like at the low redshift and high stellar mass regime, the accretion channel may become important compared to the accretion channel. Okay, and also we found that another interesting result, that about 20% of the supermassive black hole mass is actually not in the center, not in the galaxy center at the redshift of 0. That's because when two galaxies merge, they may undergo their supermassive black holes undergo a long journey before they finally reach together and merge into a single one. And if the time is too long, then the supermassive black holes will never merge and become a long-lived wandering supermassive black holes that are not at the center of the merged galaxy. And we predict that at the redshift of 0, about 20% of the supermassive black hole mass is actually locked within this so-called wandering supermassive black holes. And this fraction actually highly depends on the stellar mass. That means the more massive galaxy is, the larger the fraction the wandering supermassive black hole is. And that's the main results. And just as a quick summary, we provide the best measurements of the black hole accretion rate as a function of stellar mass and the redshift, and also the accretion distribution. And with this result, we can certainly obtain lots of scientific insights in various of topics. And these results has already been published and already publicly available. And in our recent work, we also combine that with the TNG simulation so that we can predict a realistic supermassive black hole population evolution from redshift 4 to redshift of 0. And I will stop here and happy to take any questions. Thank you.
All right, thank you very much, Fan. Again, we have a few minutes for questions. Please feel free to do the raise hand function or drop it in the chat. First, I see Rich, your hand is up.
Yep. So have you integrated your data to see how it matches with the observed X-ray background flux luminosity? That's
You
an
mean
integral constraint on the models.
you mean like basically it's like similar to the X-ray luminosity function?
You have to integrate the X-ray luminosity function, overall cosmic time, accounting for redshifts, and trying to reproduce the X-ray background, its flux and its spectral shape.
Okay, I see. Yeah, we haven't done that actually. Yeah, that's a good point. We can like I think that such an exercise is straightforward. Just integrate that to get the CXB.
Right, but it's critical because it's integral constraints are very powerful.
Yeah, that's a good point. We haven't done that, but I would certainly try that. Thank you.
You're welcome.
Okay, we also have a question in the chat from Paolo Capi. First, nice work. And then what do you do about the contribution from heavily obscured accretion, which is not well constrained by Chandra and eROSITA?
Yeah, that's a very good point. So I have to admit that there is very little we can do about that. We only use the actually observed X-ray emission, so I presume that's mostly from the Compton scene AGNs, and we think we still miss some part of the Compton thick growth, and we have thought about actually very carefully, and I don't think currently we have very good solution for that. But there are some work comparing like the JWST measured black hole accretion rate versus the X-ray measured black hole accretion rate, accretion density, and it has been shown that they only differ at about ratio of 3, but below that they are mostly consistent. So that may indicate that the black hole, the Compton thin accretion is generally fine at the relatively lower redshift below 3, but at high redshift, we are certainly missing that. Yeah.
Can I interject just to comment on follow up on that question? I was wondering if that could explain the difference that you saw between the predictions in the Lustre simulation and what you're measuring. The fact that you don't have the contribution from the obscure AGNs.
Yeah. So here, I would think that there's some work just comparing the simulation with the observations far beyond this plot, and they have shown that even after considering the Compton thick fraction, their TNG modeled accretion is still far above than the observed accretion. So I think that's kind of like a fundamental limitation for the simulation, not just because our lack of the Compton thick agents.
Okay, thanks, Fan. There are a couple additional questions in the chat, but we actually need to move ahead to our next speaker. So thank you again, Fan. Great job.
Okay, thank you. I will. Yeah.
Oh, yep.
Yeah, I will try
to
answer
look
that
at the chat and you can answer.
Yeah.
Okay, and then we'll go to our third and final speaker for today, which is Julia Buck-Motzkin, a PhD candidate at Harvard. So Julia, again, feel free to share your screen and start up when you're ready.
Hi, thank you so much. Can you see my screen?
Not yet, no.
Yeah, not yet.
There we go.
Okay,
there you go.
Mm-hmm.
Okay, thank you so much for having me. This talk is a little bit of a departure thematically from the previous two. I'm going to be talking about first searches for heavy neutral leptons in IceCube. And don't worry, I will explain what both of those things are. To start though, we need a little bit of background on neutrino oscillations. For those of you who may not be familiar, neutrino oscillations are the phenomenon whereby neutrinos of one flavor, so electron, muon, or tau, because the neutrinos come with a charged lepton partner, when they travel, they can actually turn into flavors of another kind on detection. So neutrinos start off as, say, an electron neutrino, and then as it travels in its mass state. That's mass, we label them 1, 2, or 3. And as it travels through the Earth, it's going to be mass 1. And then a mass 1 neutrino, upon interaction, has a certain probability of interacting as an electron, muon, or tau neutrino. And this phenomenon was discovered pretty early in the days of neutrino detection experiments, where flavor-sensitive atmospheric neutrino experiments, which measure the neutrinos produced by muons, which are in turn produced by cosmic rays, were actually noticing a deficit in the number of muon neutrinos compared to expectation. However, measurements that were flavor agnostic, so would identify an electron, muon, or tau neutrino all the same, noticed that their flux exactly matched the predicted flux. And this data, including several confirmatory experiments, led to a really thorough understanding of neutrino oscillations. And this is mostly good news, unless you had thought the standard model of particle physics was complete, because the standard model doesn't include neutrino mass. And the neutrino oscillation, because it depends on the difference between the mass squared states, obviously implies that neutrinos have mass. On top of that, the neutrino mass is restricted to be much, much lighter than the mass of any other standard model particle. Our most recent data from the DESI experiment actually use cosmological data, usually based on Big Bang nucleosynthesis, to place bounds on the neutrino mass of the sum of the 3 neutrino masses being about 0.07 eV, so 1,000,000 times smaller than the mass of the electron. In the standard model, neutrinos have 3 permissible interactions. They have the kinetic term, which means they travel through space. They have a charged current interaction term. This is a weak interaction whereby they can change flavor, separate from oscillation. And then they also have neutral current interactions, where they just scatter off something else. This is also a weak interaction, but there is no flavor change. And you'll notice there is no mass term here because, again, neutrinos don't have mass in the standard model. And if you want to give them mass, the first natural choice is to include a mass term that looks something like this, which is similar in structure to the mass term of every other particle that we know about. From left to right, you have a Yukawa interaction. That's the interaction that actually gives the particles mass. Then you have the lepton doublet. So that's the neutrino in its flavor state with the charged lepton, either an electron and an electron neutrino, muon neutrino, or a tau neutrino. You have your Higgs boson, which is a byproduct of the Yukawa interaction. And you have a sterile neutrino. This means that in order to add mass to neutrinos, you have to add a new particle, this sterile neutrino. And with a little bit of massaging, you can get this to a statement of the mass that looks more intuitive. You're treating these particles as Dirac particles, which just means they're kind of normal in particle physics terms. And because of the Yukawa coupling and because the neutrino mass is so small, this means that the Yukawa coupling needs to be 10 to the negative 11th times the Yukawa coupling of other particles, which are normally around order 1. And if you're a particle physicist and you're concerned about naturalness, which is something we tend to be very concerned about, this sends all of the alarm bells ringing. Because though neutrinos are unique, they're not exceptional in terms of the way that they interact with other particles. And so it would be very, very strange for them to have this exceptional coupling for no apparent reason. If you want to fix this, one thing that you can do is allow neutrinos to be their own antiparticles. This would mean that neutrinos are Majorana particles. This would also imply that you need to add a right-handed neutrino or a sterile neutrino, and you would have a Majorana mass, similar to the previous term we saw. But this one isn't Lorentz invariant, and all of our Lagrangians in quantum field theory need to be Lorentz invariant. So you can bypass both of these issues by combining the Dirac and Majorana terms, which means neutrinos will have this funky kind of quasi-Dirac, quasi-Majorana structure. and end up rewriting the mass in a way where the active neutrinos have a mass of the Dirac mass squared over the Majorana mass, and the sterile neutrinos just have the Majorana mass. When you do this, the more massive the sterile neutrinos are, the lighter the active neutrinos become. And we call this the seesaw mechanism. It is one of the most kind of common theories behind neutrino mass generation, and the more sophisticated models that are out there tend to build upon this basic concept. When you do this, that sterile neutrino becomes much heavier than the active neutrinos, so we call it heavy. It's sterile. This means it doesn't have any weak interactions, in addition to, like all their neutrinos, not having electromagnetic or strong interactions. And it's a lepton like the other neutrinos. And so we term it the heavy neutral lepton. And this is what we're looking for. Now, you might ask, if the search is so well motivated and the theory is so common, why are you looking for it? Shouldn't someone else have looked for it before? And there are pretty strong constraints on HNL existence, and they tend to come from 3 places. So to just outline this plot, if you look at the y-axis, this is the HNL mixing. That's kind of the coupling strength or the interaction strength with an active neutrino flavor. This plot is going to portray its mixing with the muon neutrino. On this axis, because the mass of the HNL is a free parameter, you have the theoretical HNL mass. All of the shaded regions I'm about to show you are places where the existence of an HNL has been ruled out. The first thing that we use to rule this out is just the seesaw bound. If it couples too weakly or it's too light, then this HNL can't actually solve our problem, and it becomes no longer theoretically motivated. Then you have bounds from Big Bang nucleosynthesis. If the coupling strength is very strong, then the neutrino will decay really quickly, and this will mess up your measurements of N effective, which are taken from Big Bang nucleosynthesis. Those are very well constrained to 3, corresponding to our 3 active neutrino flavors. And finally, you have experimental data. Most of this data comes from experiments that are either looking at a particle beam like the one at the LHC, or they're looking at what we call a fixed target experiment. So you shoot a bunch of particles at a metal target, which produces pions and kaons that then decay into neutrinos. And these particles tend to be long-lived particle searches. So they're generally not looking only for heavy neutral leptons. They're looking for anything that is kind of an exotic particle which can travel a long distance before decaying. And they typically don't find anything, or it would have been big news, and so they can set pretty strong constraints. And when you look at the existing constraints in the data-driven rather than heuristic way, you can see that the space is really crowded. So what are we doing here? Well, like I said, this axis shows the HNL coupling with the muon. But if you look at the HNL coupling with the tau neutrino, our space is far less restricted. In these plots, the shaded regions correspond to existing limits, and those lines to anticipated experiments. So your constraints actually really only start up here. And part of the reason that this tau phase space is so much less constrained is because taus are the heaviest particles and of the 3 charged leptons, which makes them very difficult to produce. But the phenomenon of oscillation can help us. When cosmic rays create muon neutrinos, those muon neutrinos can pass through the Earth, and as they do so, they oscillate. If you choose the right distance to energy ratio, then you can get a sample that is about 50% tau neutrinos from your initial cosmic muon neutrinos. And that is exactly what IceCube does. Because IceCube is a water Cherenkov detector, and because it's a cubic kilometer of ice, and there are really only 2 places in the world that you can get that, Greenland, where the ice isn't very pure and it moves around a lot, so it's not a great candidate, and the South Pole, where you have extremely pure ice in an extremely stable location. And so IceCube has taken one of the cubic kilometers of the Antarctic ice cap and has instrumented it with photodetectors. And so if you look in this area, these little beads each represent one of the photodetectors that makes up IceCube. And it's split into two sections. There's the main array, and then this green highlighted section, which we call deep core. Because of the way Cherenkov radiation works, the spacing of our photodetectors is pretty closely related to the energy threshold of the detector. And so in deep core, where these detectors are more closely spaced, we can lower our energy threshold and get to that tau neutrino oscillation maximum. That means that IceCube has a comparative advantage when studying HNL mixing with the tau. The picture gets a little less rosy from here, because even in deep core, at these low energies, event topologies can be pretty difficult to distinguish, which means it's going to be hard to tell what kind of particle you're looking at. Tracks are typically caused by muons, anything through going that's not going to interact very quickly. Cascades are caused by electrons, which interact very quickly, or neutral current events, where again, the particles will decay and not go very far. And double cascades can be caused by a variety of exotic signatures like the HNL. An HNL event in IceCube will start with a tau neutrino interacting with the ice, producing the HNL itself and a charged particle shower. The HNL will then travel a relatively short distance before decaying into another tau neutrino, and this is because we're looking for HNL mixing with the tau. If the HNL could mix with other of the neutrino flavors, it could produce those, but that's not what this search is. And if you're lucky, other charged particles. And when this happens, you get a very unique double cascade signature. Unfortunately, in data, this is not actually what it looks like. And part of this is because when the HNL decays, one of the dominant decay modes is to 3 neutrinos, which is completely invisible. And so this plot here shows the fraction of energy in the event, which converts to visible photons. And in the first cascade, a lot of that energy, right, this is going to peak between 70 and 90%. Most of the energy of each event is visible. However, for the second cascade, you have a much broader and much lower distribution with this peak around 0. So often you can't see the second cascade, which means we're not getting that unique double cascade topology. On top of that, the overall energy fraction is going to be relatively low, which means that in our events, which are already dancing at the low end of IceCube's detection threshold, not all of the light is going to be visible, which is going to further complicate things. And so in order to address some of these challenges, we developed an analysis approach that, rather than looking only for surefire double cascade events, divided our events into 3 categories: cascade-like, track-like, and somewhere in between. So this plot shows the signal over square root of anticipated background for 9.28 years of data. This is IceCube's longest event sample. And as you would expect, the double cascade topology ends up with most of our anticipated signal events being in that mixed region, followed by the cascade region with almost nothing in the track-like region. However, if you know the z-axis here, it barely goes up to 0.4. Our sample is highly, highly background dominated. And this plot was made with a 1 GeV HNL and a 0.1 mixing strength. This is actually much higher than is considered kind of state of the art in terms of our limits. So this is a very optimistic picture. Naturally, when we went and looked for HNLs in data, we found something consistent with a background dominated analysis, and that was that you can see hints of an HNL potentially existing, but we're so background dominated that you can't say anything with a high degree of certainty. And within 3 sigma, we are completely consistent with 0 events. And so that means that our results are consistent with current limits, but not world leading. And I think this is actually really exciting. And that's because the next steps in this analysis, and you'll be able to see the current steps in a publication which is currently in preparation, but the next step involves a GNN reconstruction of these actual HNL events. So by leveraging the neural network, rather than using pre-existing IceCube reconstruction tools, we're going to be able to distinguish the double cascade events themselves. And while we don't anticipate that this is going to be a large percentage of our overall signal, by dividing the analysis into a cascade-like excess search, like the one we have here, and on top of that, adding the non-background dominated double cascade search, we're going to improve our sensitivity at least threefold, probably more. Second, at the moment, you'll notice that most of these limits stop at an HNL of about 1 to 2 GeV in mass. And that's because there have been simulation challenges for simulating HNL decays when they have a higher mass because of the number of mesonic decays that are opened up. But we're going to expand our simulation to accommodate those masses. And so we're going to be able to push further, not only down in this direction, but also in this direction. And finally, the IceCube upgrade, which is anticipated in the next 5 to 10 years, is going to create more detector infill. It's going to make our detector a little bit more densely packed, which is going to lower the energy threshold for the detector overall, and is going to help us address some of those fundamental detection challenges. Thank you so much. I'm happy to take questions.
All right, thank you, Julia. Same as before, please use the chat or the hand raise for questions for Julia. Okay, we have a hand raise from Vanessa.
Hello, Julia. Thank you so much for the talk. Very interesting. You know, I'm always interested about the IceCube results. So just a simple question. So why are you interested in the tau flux as opposed to the other particles? What is so special about the tau interaction?
There are two reasons. The first is, like I said, it's just a lot less constrained. So there's less that we know already about the potential HNL mixing with the tau. But the second is, if you look at the way that other neutrino couplings work, it's typically not coupling only with one of the other flavors. They usually couple with all three in some proportion. And that means that if the HNL exists, that is what's most likely. But you can't constrain it as strongly if you look for all of these couplings simultaneously. By doing a tau neutrino specific search, what we can do is really hone in on the coupling with the tau, and then other experiments which have muon neutrino dominated beams or electron neutrino dominated beams can look at that. In IceCube, you can also pretty well isolate muon neutrino events by looking for things which are downgoing. So what I showed you, these are all upgoing events, which means they enter through the bottom of the detector, that's through the northern hemisphere, and they go up. If you want to look for mostly muon neutrino events, you can use the downgoing events because those just don't have enough distance to oscillate very much. And so you get a relatively pure signal. So if you can combine those two, you can get a kind of dual constraint. But in order to do that, you need to be able to do one of them really solidly first before you can combine them. So this is a first step to more thorough searches.
Okay, yeah, thank you so much.
Of course.
Okay, thanks, Julia. That's actually taken us right up against the hour here. So great job, Julia, and great job for all of our speakers. And thank you, everyone, for joining us. As I mentioned, we'll be doing these every couple of months or so with 3 new talks each time. And just before we close, I'm going to drop into the chat a link to the Frontier Seminar website and also a link to the nomination form. So if you are attending and you feel like you'd like to give a talk in the future, or if you would like to nominate someone for a talk, please feel free to do so. And we will be back again in a few months. Thank you, everyone.